Okay. Thank you very much to the organizers of this conference. Yeah, so I'm very happy to tell you about this recent result, which is on a quantum algorithm for Khovanov homology, which is joint work with Aaron Lauda, who was just here, and Seth Lloyd at MIT, and Michelle Riley at MIT, and Paolo Zanardi at University of Southern California. And I think I have to start with a disclaimer, which is I am not a topologist. I'm a quantum information theorist. So we try to think about how we can use quantum physics, quantum computers, to help us solve problems in abstract mathematics or in computer science. But this whole community of quantum information theorists has always been very interested in topology for several reasons. For example, topology has informed a new way for us to understand quantum computation, which is called topological quantum computing. And it's also actually a new model that we use, a new proposal of actually building these quantum computers as physical systems. They have inspired ways to do quantum computation in error-correcting, in an error-robust way by encoding information in some topological degrees of freedom. So for example, in the homology groups of a torus. The idea here is that these degrees of freedoms are non-local, whereas physical noise is usually local. So the information cannot be destroyed by physical noise. And importantly, it has also inspired new quantum algorithms. So new applications of quantum computers that are justifications for actually building these devices. So new quantum algorithms that achieve exponential quantum speedups for approximating certain topological invariants, for example, knot invariants. So let me just give a quick example of this. So a very famous knot invariant is the Jones polynomial. And one could ask, okay, in a complexity theoretic sense, in a computational sense, how difficult is it to approximate the Jones polynomial of a given braid, or the closure of some braid, at a fixed root of unity, for example, the fifth root of unity? And the answer is, perhaps surprisingly, this problem is exactly as hard as simulating a universal quantum computer. So I'll explain in a second what a quantum computer is. For now, it's just some physically realizable model of computation, which is built on quantum physics, so it's believed to be strictly more powerful than classical computing, which is what this laptop does, for example. And simulating a quantum computer means predicting the output of the quantum computer given the input. So this is a quite old result, over 20 years old. This is first due to Friedman, Kitaev, and Wang, and then later it was refined by Aharonov, Jones, and Landau. So with that in mind, here's the talk. I'll just give a very brief crash course in quantum information. So I'll explain very briefly what is a quantum computer, how does it work. Then I'll explain why it's interesting for applications in topology. So I'll review this old result about how quantum algorithms can efficiently approximate the Jones polynomial in a regime where no classical efficient algorithm exists. And then I'll talk about our main new result, which is a quantum algorithm not for the Jones polynomial, but for its categorification, so for Khovanov homology. And I'll conclude with some open questions, and in fact, there are many of them. Okay, so maybe first as a motivation, what are quantum computers and what are they good at? So it's really just based on the simple observation that if you're trying to simulate quantum physics, that turns out to be exponentially hard for classical computers. And the observation here is that if you take the composite of two quantum systems, the Hilbert space that they live in is the tensor product of the individual Hilbert spaces. So the dimension grows exponentially in the number of systems, meaning just to describe a state of a, let's say, n quantum systems system, you need information that grows exponentially in n. So quantum physics is exponentially hard to simulate classically, so it should somehow have some computational power that is exponentially better than what classical computers can do. And the obvious thing that they're good at is they're good at simulating other quantum systems. So in quantum chemistry, for example, if you're trying to figure out the free energy of some molecules or something, that's something that quantum computers are good at. But really, the much more interesting thing is they also happen to be good at problems in mathematics which seem to have no connection to quantum physics at all. So famously, Peter Shor at MIT, he realized that you can use these quantum computers to efficiently factor semi-primes, so for efficient integer factorization. And we don't know any efficient classical algorithm that achieves that task. They're also good at some specific linear algebra problems. The reason for that is basically that quantum physics is linear, quantum mechanics. And crucially, which is the topic of this talk, they turn out to be good at approximating certain topological invariants. And this picture I stole from Peter, who I think is not here, so that's good. Okay, so a minimum of explanation of what these quantum computers are. So they're built out of qubits. Qubits are just normalized, they live in C2, and they're described by unit vectors in C2. So a qubit state is usually written like this: a superposition of two basis elements with complex coefficients where the coefficients are normalized. And we use this bracket notation, but you can understand this purely in terms of linear algebra by just assigning some basis vectors to these bar and cats. And if you have n qubits, then these are just unit vectors that live in the n-fold tensor product of C2. So those are the building blocks, and then a quantum computer acts on those building blocks by what's called quantum gates, which are just unitaries. So they preserve the normalization. And in theory, it could be any unitary, but we always break it down into much smaller unitaries that only act on 1 qubit or 2 qubits at a time. So they're 2 by 2 or 4 by 4 matrices. And here are some that we like for various reasons. So the Hadamard is a 1 qubit gate. The C0 is a 2 qubit gate, which, conditioned on the state of the first qubit, it flips the 0 and 1 state of the second qubit. And quantum circuits are just sequences of quantum gates. So one could write this in this matrix product form, or we typically write it as in the circuit diagram, where time goes from left to right, and we just sequentially apply gates to the qubits, which are initialized in some product state, like the all-zero state. So here the H is just a Hadamard, a 1 qubit gate, and this weird line is a C0, where the control is given by this symbol, and the action is given by the plus. So this is a 2 qubit gate. Okay. So let me give, so we say circuits are efficient if they are short, so they only are composed of few gates, meaning polynomial in the input sides. So let me give the simplest useful example. And actually later on I will explain these circuits in a more, I think, topologically friendly way. But for now I'll use the circuit description. So you can choose later on which one you prefer. But the simplest non-trivial circuit, quantum circuit, is what's called the Hadamard test, which is a way of, given some unitary U, so given some quantum circuit U, estimating a given matrix element of it. So V, U, V, where V is some initial state. So this is how it works. This is the circuit description of that Hadamard test. And I'll just walk you through step by step. So the first step is you prepare this input state V in one system, and you prepare another qubit, which we call an ancilla, in the 0 state. Then you apply a Hadamard, so this gate I explained earlier, to the ancilla. You apply a controlled quantum circuit, so that means you apply the unitary only to the part of the state where the ancilla is in the state 1. And if the ancilla is in the state 0, you don't do anything. So this is the resulting state you get. Then you apply a Hadamard again to the ancilla. And then you measure the ancilla in a computational basis, which just means, in this context, if the ancilla is in the 0 state, you apply a +1 to the system, to this part. If the ancilla is in the 1 state, you apply a -1. And you can see that now you get, sort of here you have the identity plus U, here you have the identity minus U. If you measure 1, then you take the difference, which is U minus U dagger. If you measure a 0, you get the sum, which is U plus U dagger. And in expectation, you obtain this matrix element, which is the real part of the actual matrix element you care about. And it's easy to modify this test to also estimate the complex conjugate of that. So this is a simple quantum circuit for estimating matrix elements. Okay, now, yeah.
Since I have no idea what's going on, really, I mean, why wouldn't you have just had V by U and then test it against V?
Yeah, the reason is it's unclear how to do this test against V. So,
I see.
yeah.
But, I mean, so you don't know what V is somehow.
You know what V is. Let's say you know what V is. You prepare it initially.
Yeah.
And then you can't really, the thing is, testing against V is, it's unclear how to do.
Observable isn't somehow, it's the zeros and ones, right?
Yeah. Yeah.
Those are the measurements you're allowed to make.
Yeah, yeah, yeah.
Okay.
Yeah, yeah.
What is the slash below the first line?
This just means that I only draw one line, but it's not just one qubit, it's many qubits. Yeah. Yeah. Thank you. Okay, the next slide I think will make much more sense because it's sort of more topologically friendly, which is another interesting algorithm for estimating the Jones polynomial. So I'll review these earlier results from the early 2000s. So let's say you have some braid, and you're trying to estimate the Jones polynomial of some closure of that braid at a root of unity. So this quantum algorithm doesn't work for arbitrary Q or T, but at a root of unity, the representations of the braid group derived from quantum SL2 are unitary itself. And moreover, they act on some representation space which is finite dimensional. So I could think of it as the state space, the Hilbert space, of finitely many qubits. So that means this braid, so the associated unitary operator arising from this representation is some unitary. And it decomposes in the sense that it is a product of unitaries for each crossing in a braid. So I can just think of this picture as being a quantum circuit that acts on some qubits, and each crossing is one unitary gate. And if I want to estimate the Jones polynomial of that, of some closure of the braid, let's say the Platt closure, then this is just given by some specific matrix element of that unitary operator, which is now just a matrix element of that quantum circuit, which you can efficiently compute using the algorithm I explained earlier. Alternatively, if you want the Jones polynomial of the trace closure, that would just be the trace of this unitary, of this quantum circuit, which, again, there is an algorithm, a quantum algorithm for efficiently estimating that trace of the quantum circuit. Essentially, what you do is you do this Hadamard test to estimate matrix elements, but you do it many times for randomly chosen matrix elements, and then that will, the expectation value of that will be the trace. Yeah?
So this is the same algorithm as on the previous slide. You're just using the matrix, which is the image under the braid representation?
That's right. It is, but sort of this part is highly non-trivial in the sense that now it solves a completely different problem. Now it solves the problem of estimating the Jones polynomial at a root of unity. Whereas before, it just acts on some arbitrary quantum circuit, and it took many years to figure out that you could use this Hadamard test to actually estimate the Jones polynomial. Yeah?
Sorry, so if I understand the setup correctly, you have an input qubit, I guess,
Yeah.
each strand, and then at each crossing you have some operator.
So it's not exactly one qubit for each strand.
Okay.
The actual mapping is a little bit more complicated, but it's some finite dimensional space that they act on, so I write it in terms of qubits.
All right.
Yeah, each crossing is some unitary operator.
And you know what this unitary operator is?
It's the, I think you call it the R matrix.
Yeah.
Yeah.
Oh, okay, fine.
Yeah. Yeah. Okay, so in particular, yeah?
Thanks.
Okay. So this is just some kind of quantum algorithm for estimating the Jones polynomial. actually, the whole story is much more interesting, which is this is a universal algorithm, meaning any quantum computation you can reduce to simply estimating the Jones polynomial at some root of unity. And the way to see that is basically that for high enough roots of unity, let's say the fifth root of unity, these braid group representations are dense in the space of quantum circuits, meaning by multiplying together R and R inverse, etc., you can actually, in polynomial depth, approximate any quantum circuit. In other words, any quantum circuit can be, simulated by just sort of writing down a corresponding braid, estimating the Jones polynomial of that braid. So this implies an exponential quantum speedup for the Jones polynomial in the sense that we have an algorithm that efficiently approximates it. And also, there can't be a classical algorithm that efficiently approximates it to the same accuracy, because otherwise you could use that classical algorithm to just simulate all of quantum physics efficiently, which we believe is not true. Good. So this was a major breakthrough 20 years ago. It's one of the few exponential quantum speedups where we can actually have very strong evidence for the fact that they do provide an exponential quantum speedup. There's a physical way of understanding why quantum algorithms should be good at estimating the Jones polynomial, which is that the Jones polynomial appears as an observable associated to the expectation value of Wilson loop observables in 3D Trent-Simons, so in certain TQFTs. And at least naively, one would think that quantum computers should be able to efficiently simulate quantum field theories. So they should be able to efficiently predict observables in those topological quantum field theories. And indeed, this line of thinking is how these quantum algorithms for the Jones polynomial were first developed by Friedman, Kitaev, and Wang, by trying to think about quantum algorithms that simulate topological quantum field theories. Okay, now, the Jones polynomial is, of course, just a shadow of a much richer not invariant, which is Khovanov homology. And interestingly, this physical connection at the decategorified level, it extends, or it is at least believed to extend to the categorified level. Meaning that Witten has some papers arguing that, again, Khovanov homology one can understand as, it is associated to certain surface operators, surface observables in a higher dimensional TQFT, which is now 4-dimensional super Yang-Mills theory. So this diagram raises an obvious question, I think, which is, okay, can you still use that physical connection at the categorified level to obtain exponential quantum speedups for simulating or predicting the Bethe numbers of Khovanov homology? And surprisingly, we're the first one to study this, and that's what I'm going to talk about now. Okay, so I definitely don't have to explain to this room what Khovanov homology is, but let me just attempt to define it to establish some notation. So it's a bi-graded homology theory whose graded Euler characteristic is the Jones polynomial, meaning for any diagram of a knot or a link, it associates some chain groups indexed by homological and quantum gradings. There is a boundary map acting between those chain groups, which I'm not going to write down. This defines homology groups in the standard way. These homology groups each homology group is by itself a topological invariant. And the Jones polynomial is recovered as the graded Euler characteristic of this homology theory. So we would like to design a quantum algorithm that can efficiently compute these homology groups. So it could calculate the generators of that group, or maybe just the dimensions, so the Bethe numbers of Khovanov homology. So at first, it seems completely unclear how to do that. Once you go to Khovanov homology, you can no longer fix T to be a root of unity. So there's no unitary structure anymore. There is no obvious connection to quantum circuits at all. Sort of everything I've explained previously breaks down. There's also no obvious connection to the Hadamard test or these other existing quantum algorithms. So we really needed like a key new idea, which we take from Hodge theory, which says that these homology groups, one can rewrite them as the kernel of some linear operator, which is called the Hodge Laplacian. So probably this is a bit weird for this audience because I think usually you think with Z grading, so with Khovanov homology over Z, but we can just think of it over a higher field, over the complex numbers. This matrix will have integer entries, but we can think of it as a matrix over the complex numbers. And then this Hodge relation is well defined. Okay, so finding the Khovanov homology groups is equivalent to finding the kernel of some linear operator. And this linear operator is not just arbitrary, it is Hermitian, so self-adjoint, which is easy to see, which means in physics we can think of it as a Hamiltonian. It's also positive semi-definite, which is also easy to see, meaning the kernel of that Hamiltonian is actually the ground state space of that Hamiltonian. It's the lowest energy space. It is local. That's essentially because the boundary operator is local, because it acts locally on crossings. And in fact, this Hamiltonian is even supersymmetric, and that's just sort of, I mean, for a supercharge which corresponds to this boundary operator, by definition, this is a supersymmetric Hamiltonian. So all these things are very nice from a physical perspective. This means that computing Khovanov homology is equivalent to preparing the ground state of some supersymmetric quantum Hamiltonian, of some supersymmetric quantum system, which is moreover local. Yeah? It's maybe not too important. It's just so in physics, Hamiltonians of the form Q dagger Q plus Q Q dagger, we call supersymmetric. So this is of this form. This Hamiltonian is of this form if you just replace Q by the boundary operator. Yeah. So in particular, I mean, in supersymmetry, whether or not the kernel is empty or not, so whether there exists a zero energy state or not, is called whether there's spontaneous supersymmetry breaking. So in some sense, checking whether the Khovanov homology groups are trivial or not, are empty or not, corresponds to checking whether there's supersymmetry breaking in this Hamiltonian. Okay, so again, punchline. This is now a state that seems much more sort of natural in the language of quantum computing. And this idea is actually, you could think that this Hodge theory, it applies for arbitrary or for many different homologies. And indeed, this idea is not new. So Seth Lloyd and Silvano Gannerone and Paolo Zanardi, in 2016, they wrote down quantum algorithms for computing the ranks of clique homology and other simplicial homologies using just this idea by like mapping them to the ground state of some Hamiltonian and preparing that ground state. I should say maybe that preparing the ground state of a Hamiltonian is a very natural thing in physics. So I mean, nature does it all the time. Like the reason why your coffee from earlier is cold is because the coffee has coupled to the thermal bath. The thermal bath moves it towards its ground state, which has a lower temperature. Yeah.
Can you use the same strategy to compute the coefficients of the Jones binomial, or is that easier or harder?
You can, yeah. So this is strictly harder in the sense that once you have the Betti numbers, you just take your alternating sum essentially, and it gives you the coefficients.
You can do that. Okay.
Yeah. But there are details as to when our algorithm is efficient. Because this problem is strictly harder, it's not always going to be efficient. Okay, so this, as I said, this idea has been used previously in a different context for clique homology. Clique homology is some kind of homology that turns out to be interesting for computer scientists because it appears in what's called topological data analysis. And there have been many follow-up works on this, including some by me. But applying it to these knot invariants is new. So here's how the actual quantum algorithm will look like. So the goal is to prepare the ground state of this, what we call Hodge Laplacian. So there are many possible approaches for doing that. One is what I sketched earlier, is just thermalization. So somehow coupling to some thermal bath, using the fact that nature naturally cools down Hamiltonians. There are more sophisticated ways of doing so, more sophisticated quantum algorithms. One is called quantum phase estimation, which essentially projects into the ground state. There's another approach which is called adiabatic quantum evolution, which turns out in physics, if you start in the ground state of some system and you change the system Hamiltonian very slowly, the state will remain in the ground state. So you could start by preparing the ground state of some easy to prepare Hamiltonian, and then slowly change that Hamiltonian to the Hodge Laplacian, and then you would have arrived at the ground state of that Hodge Laplacian. So I won't say much about sort of the details of how these algorithms work. I'll briefly talk about the one that we actually use in our paper, which is this formalization idea. And I'll just give some slightly additional motivation for how it works. So standard in quantum physics, states evolve according to this Schrödinger equation. So they evolve like e to the minus iht. Now, if you could choose the time to be imaginary, then instead you would get this kind of evolution. So if t you choose to be I tau, or minus I tau, you would get this kind of evolution, which exponentially suppresses all eigenstates of the Hamiltonian which don't have zero energy. So as you increase the time, this system evolves towards the ground state of H. And that's exactly basically the approach we use in our paper. We do time evolution, but with imaginary time to move towards the ground state, which is equivalent to these homology groups. So I won't write down the algorithm. I'll just say that the complexity of this, so how long does it take to do this, depends essentially on two quantities. One is some abstract quantity, which is called the formalization time. And the other one is the inverse of the spectral gap of the Hamiltonian. And the spectral gap is the smallest non-zero eigenvalue of that Hamiltonian. And you can see here that if the spectral gap is very small, so if there's some eigenstate which has energy that's only slightly above zero, then this state you will have to evolve for a very long time until you lose support in that state. So this is why the spectral gap enters. So really, a main sort of math challenge of our project was to say anything about the spectral gap of this Khovanov Hodge Laplacian. And the first problem is the spectral gap is not topologically invariant. So if you have two different representations of the same knot, then they might have different spectral gaps. And indeed, the simplest case to illustrate this is you just take the unknot and you twist it n times. And you still have the unknot, but in some different representation now. So what's the spectral gap? Well, we just computed, and it turns out to decay with the number of twists. And what is this function? Well, it happens to be this. Yeah, I don't know. I mean, I'm hoping that maybe some of you could help us with figuring out where this comes from. So that's a big issue. We cannot characterize the spectral gap independent of the representation. What we would like to show is that the spectral gap decays only inverse polynomially in the system size, which in this case is the number of crossings of the underlying knot. And the reason for that is that if that spectral gap only decays inverse polynomially, then this function here is some polynomial, and we say an algorithm is efficient if the time is polynomial in the input size. So for the unknot, this is true. So this only decays like 1 over n squared, so this is fine. But of course, we would like to prove this in general. Something that Aaron did is he just exhaustively computed the spectral gap using some knot library for all knots with 11 or less crossings, and also for some links. And we plotted here, I mean, the fits are really bad, but we plotted here the average spectral gap, meaning for each knot, we average over all homological and quantum degrees, and look at how big the spectral gap is. That's on the left. And we also plot the minimal spectral gap, meaning we minimize over all homological and quantum degrees, and again, look at how big the gap is. And the good news is that the gap seems to increase with the system size, whereas our worry was that it decays exponentially in system size. And even the minimal gap only seems to decay inverse polynomially. So we don't have strong evidence for this. Just by fitting the data, inverse polynomial fits are better than inverse exponential fits. So our conjecture is that actually all spectral gaps of Khovanov homology only decay inverse polynomially in the number of crossings. To make this precise, we have another statement showing that if you just change the representation, the knot diagram by adding some twists, for example, or some other Rademacher moves, those changes only impact the spectral gap in inverse polynomial way. And Aaron has shown proven this conjecture to be true for some extremal homological degrees, so where either I or J are extremal, and only for some subsets of the families of knots. But, so yeah, that brings me to the open questions. Really, the key open question, which is going to be which we need to answer in order to prove that our quantum algorithm is actually efficient all the time. Right now, we only know it's efficient in some cases, is to prove a lower bound on the spectral gap of the Khovanov Laplacian for arbitrary knots and arbitrary q and I degrees. Other open questions are, of course, these same ideas can be used for other homologies, as I said, and it would be interesting to attempt to try them for other homological invariants that appear for knot invariants, for example, or other invariants that are of interest to topologists, like Lie homology. There are technical questions that we, from the quantum information theory community, are very interested in, which is, for example, can an arbitrary quantum Hamiltonian be encoded into the Khovanov Laplacian of some knot or link, which would imply complexity theoretic statements like QMA completeness, if you know what that is. And moreover, since Khovanov homology is related to observables in 4D super-Young mills, it would be very interesting to try to characterize the complexity theoretic hardness of simulating 4D super-Young mills. So to recap, estimating the complexity theoretic hardness of simulating 3D Chern-Simons is what led to these quantum algorithms for the Jones polynomial. Okay, and I'll conclude with what I think is the most interesting open question, which is, can you design quantum algorithms for detecting the unknot? Okay, so here's a knot, and here are different knots, which all happen to be the unknot. But given a knot diagram, figuring out whether that knot is the unknot or not is a very hard problem. The nice thing about complexity theory is that we can say in a very quantitative way how challenging this problem is, how hard this problem is. So it was shown in 1961 that this problem is decidable in the first place. So there is some algorithm that decides this, but it might have exponential runtime. And then it took almost 40 years to show that not just is this problem decidable, but it's also contained in some reasonable complexity class, which in this case is NP. So NP, very informally, it's the set of problems for which if the answer is yes, there's an efficient algorithm that verifies that answer. And then later, Kuperberg showed that this problem is not just in NP, but also containing co-NP, provided the generalized Riemann hypothesis is true. Co-NP is the complement, meaning if the answer of a question is no, then there's an efficient algorithm for verifying that. And later, Lackenby showed unconditional containment in co-NP. So this puts this problem of detecting the unknot in a complexity class, which is very interesting to us. It's NP intersect co-NP. And it's very interesting to us quantum information theorists because many problems for which we know that exponential quantum speedups exist are in this complexity class. So for example, factoring a semi-prime is also in this complexity class, and it's famously solved by Shor's algorithm. And what connects this to what I said earlier is that, of course, Khovanov homology detects the unknot. So a very interesting open question is whether our algorithm or other algorithms for Khovanov homology are able to estimate Khovanov homology to a sufficiently high accuracy to actually detect the unknown. And there are no classical algorithms known for this. So if true, that would constitute another exponential quantum speedup. Okay, that's all I have. Thank you very much.
Yeah, do you get the sense that spectral gap only sees the crossing number of the diagram? Or so, for example, is introducing an extra Reidemeister 2 the same as doing 2 Reidemeister 1s?
So you're saying with a spectral gap only sees the crossing number? That's not true. So there's certain, you can have different knot diagrams with the same number of crossings that represent the same knot but have different spectral gaps. Yeah.
Any other questions?
Anything you said about coordinate maps together?
I don't think I have anything intelligent to say. Maybe Aaron would. Yeah.
Your guys' Laplacian, what's kind of similar, but with some adjoints thrown in there maybe, to this Batson seed. Have you guys thought about the Batson seed Khovanov deformation complex?
No.
Okay, cool.
Okay. So what is that?
Yeah,
Maybe you,
Yeah, that's for later. Okay.
yeah, we'll talk later.
Yeah.
But
good question.
What's the relation between having a efficient quantum algorithm and p-intercept polynomial?
So there's no formal relation known, but for the few problems where we have very strong evidence for exponential quantum speedups, most of them happen to lie in that complexity class. So we don't know that BQP contains NP-intercept co-NP, but there are many examples of such statements.
So can you provably get an exponential quantum speedup if, say, you just want the coefficients of the Jones polynomial, but you don't care about the lot? Because that could potentially not.
That's right. Probably not. So efficiently estimating all coefficients of the Jones polynomial would be way too hard, even for a quantum computer. So you can show that. You can prove it's sharply hard, so like way beyond any physical model. And computing the coefficients is of course much harder than just estimating the Jones polynomial at the root of unity, and that is already universal for quantum computation. So we don't expect that this much harder task is also efficiently possible. Yeah.
So, do you expect this inverse polynomial bound for the first eigenvalue? Does that hold seemingly for the case of simplicial as well?
Okay. Yeah, very good question. So in the simplicial case, the role of the smallest non-zero eigenvalue is understood much better. And it's still not topological, but it tells you about sort of diffusion bottlenecks on a graph. So if your simplicial homology is a clique homology, for example, then the homology would tell you about different connected components. And the second smallest eigenvalue would tell you about sort of very sparsely connected components. So even then, there's no known inverse polynomial bound, even though it has been a sort of focus of intense study. But for subclasses of graphs, by construction, you can engineer the gap to be inverse polynomial. And one issue is that for Khovanov homology, I don't have any understanding of what the interpretation of the smallest non-zero eigenvalue.